because I knew I was going to be busy this week. And I understood most of homework part 4, because we talked about simple harmonic motion before, right? So this wasn't like completely new.
Yes, exactly.
But number 6 was confusing to me, just because I don't know where to begin, like how to approach it.
Just a second.
Mm-hmm.
So number 6. All right. So you did previous problems,
Mm-hmm.
which means you basically know the concept.
Right.
And when you started reading this problem, what first came to your mind?
Well, when we talked about the standing waves in harmonic motion, that the frequency is kind of determined by the speed and the length of
That's
the
not
rope.
the first thing that should come to your mind when you read this type of problem.
Mhm.
When you read this
The
type.
screen is very blurry. Sorry.
Again?
Yeah.
Just a second. But again, this is not what first should come to your mind when you start reading this problem. What do you think? How about now?
Great. Yeah.
Great.
Just like I'm with the eye doctor when they.
So you start reading this person. What's your first thought and what's your first action?
So I know that they're talking about tension, and I know that tension
That's
is
not
mass.
the action. What should be your very first action?
Drawing a photo.
Drawing, exactly. That's your very first action.
Mm-hmm.
And until we can compare our pictures, we can't even discuss anything else. So what's happening? We've got like a string, so it should be stretched, attached somewhere and stretched. Well, we've got a pulley. Doesn't have to be. This is actually a very standard lab setup, but we're not going to do that. And then it's controlled by a weight. This is what we have. This is actually PY105 stuff so far.
Right.
There's force of gravity acting on the weight and force of tension that holds it. And clearly the same tension will be inside this spring. Well, direction will be horizontal, but the magnitude is the same inside the string as we learned. And you have your specific distance, which is what?
My distance is 129 centimeters.
And now there is a generator, electromechanical vibrator device, which we saw once actually in PY105 when I was discussing the resonance, a ball on a string.
Right.
But now we use the same device to excite oscillations in this wave. Basically, it's just a vibrator that makes it move up and down, up and down, up and down. And the frequency is set to a fixed value, 120. And you attach a weight number 1, which your mass is?
It's 235 grams.
235?
Yeah.
And in this case, what you observe is the third mode. It even gives you a hint, 3 loops. So if you take a photograph of this, a snapshot, when the wave, the string, is at the maximum displacement from equilibrium, this is what you see.
Right.
All right. What can you calculate right now? Just don't think about anything else. Just what can you calculate?
Tension is mass
Tension.
times gravity.
What else?
You could calculate the speed, right?
How?
Since you know the frequency. Well, you know the frequency, and you know that it's the third standing.
So what can you calculate first?
The speed of the the wavelength.
The wavelength, exactly.
Yeah.
You're skipping steps. We can't skip steps.
Okay.
So, and now when we know the wavelength and frequency, yes, we can calculate speed. That,
Okay.
and you don't have questions about that part, right?
No.
So what equation did you use for speed?
The one that they had in the textbook was frequency equals 3 times speed over 2 times length, because you know.
Well, okay. So the speed in a wave is just equals wavelength divided by period. This is distance over time, basically.
Right.
Or because period and frequency are related, it's just this product. Now, how did you find the wavelength?
The wavelength, in its third standing mode, there's 1.5 waves.
So this
right.
will be 1/2 of a wavelength.
Yeah.
This will be 1/2 of a wavelength. This will be 1/2 of a wavelength. So if you get 3/2, you get the total length. Basically, that's it. That's how you do it.
Okay.
From the picture. And now you can calculate the speed. You get your number, whatever it is. But did you find another equation for the speed? Speed of a wave on a string. If you Google, what does it say?
Let's see.
Speed of a wave on a string. Because we didn't cover it yet. Your best source is Google. So
yeah, there's one that has tension.
Exactly.
Yeah.
So if you know this number, probably it's supposed to be used in some way.
Right.
So probably it's supposed to be an equation, and that equation tells you tension, well, magnitude divided by what?
Divided by the string mass, which is also divided by string length. So like divided.
This is density. Yeah. This is basically the linear density of the string.
Right.
Now.
And that appears. Oh, okay, yeah. So that's that. And then the frequency is that divided by 2 times the length. But.
Well, the frequency is wherever it is. It depends on the mode. For the third mode, that's it. This is the third mode. The third mode, the third frequency, everything is third. But the speed equals to related to tension. Now what you do? You now changing the weight, correct?
Right.
To a new value, and that changes something on a string. This is what you're looking for, M2. And what's new about string?
It's in its second standing wave.
Exactly. What about frequency?
The frequency would have to, wait. It's the same, right?
It is the same because in this problem, the frequency is being set by the generator and we don't change it.
Right.
So the frequency is the same as before, which is good. But now the profile of a wave is different. Now it will look like this. So now you've got a new wavelength, and that will be the wavelength of a second mode for this particular string. So technically you should divide everything like this. Well, and this is PY105.
Right.
So what will be your new wavelength equal to?
It's equal to the length divided by 2. Or no, it's just the length.
It's just the length.
Dumb. Yeah.
Because
Okay.
you've got 1/2 of a wavelength here and 1/2 of a wavelength here.
Right.
For the second mode, there's the length. So, and well, you see the length. This variable relates case number 1 and case number 2.
Right.
So technically, I forgot, and that's not a good thing. I should have written M1. And by the way, you can combine these two equations.
Right.
Because this has to be equal to this, and this is equal to this. So I'll try to fit your equation. For the first system, will tell us that a wavelength, which is 2L/3 times frequency, which is 120, should be equal to square root of tension also 1. Oh, I'm sorry. I made a very silly mistake. This is tension number 1, and tension number 1 equals mass number 1 times G. And this is my mistake. What does this little m mean?
That's mass. Well, in that equation, it's the mass of the string, not the mass of the.
Exactly. So, and instinctively, I used the wrong symbol. So this is the equation number 1. And now you can write the same equation for the second case. Some things will be different, some things will be same. So for example, definitely G will be the same. Frequency, capital L, which represents length, will be the same. What about little m? Will be the same or different?
For the mass of the string?
Yes.
That's the same.
Exactly, same. But there will be difference. The difference comes from new mass. And also this coefficient is different. So this is your immediate goal right now. You need to write this equation and solve these two equations for the mass number 2. Can you do that?
Right. Well, if they're the same, you could just cancel out. If I wanted to equate.
Well, of course, you can do that. And by the way, your answer should be in grams, not kilograms.
Okay.
Yeah. So try it.
All right.
So you can finish it later, and maybe you have another questions.
I think I'm good. I think that was my only question, but I'll work on this now. And if I'm still stuck, you're here till 12:30, right?
Yeah, and someone else picks up it later.
Okay. I should be done by 12:30. So if I have any more questions, I'll be back by then.
All right. Good luck. Let me know anyway, you know.
Yeah, definitely.
Thanks.
Thank you so much.
All right.